All right, momentum and collisions. This is chapter 5, but still part of the second unit. So typically it's called energy and momentum, that second unit. Yeah, we're looking at momentum and impulse, which is a very important concept, and you'll see why soon here. So momentum, you've undoubtedly heard the word before. It's used. I'll put down here. It's used kind of colloquially, if that's the right way to say it, in the English language a lot. Like a hockey team has momentum if they've won a bunch of games, or sometimes you'll hear it used completely inappropriately in a pseudo science explanation. So they'll be like, something happens, oh, it's because of momentum and stuff. They're not really citing momentum as a cause for a physical phenomenon. It's just a way of sounding like they're explaining things because they're using a fancy word. So watch for that. The idea of momentum is in physics. Say, I like to ask students, if an object's flying at your head, what are 2 questions you need to ask to determine the level of danger? I think pretty obvious if you think about it. You're like, okay, something flying at your head. What are some things you're going to want to know, how you should react, right? And so one would be, of course, what the mass is, because if it's more massive, it's more dangerous. But the other factor would be the velocity, right? So this would describe, what you might think of as like the quantity of motion, or essentially how dangerous it's going to be. And so that's really momentum. Momentum is to do with mass and velocity. And so the amount of momentum is proportional to the mass, and it's proportional to the velocity. So if there's more mass or more velocity, the momentum or the quantity of motion gets bigger. And so really you just have a proportional relationship, just momentum equals mass times velocity. Yeah, I was going to think about like proportionality constant, but they must just calibrate as a 1 basically. If you're looking at the units for this, you've got kilograms and you got meters per second. So it's kind of a weird unit, kilogram meters per second, which no one really ever kind of thinks about or says much, but I mean, it's units for momentum. So an important fact about momentum, always, always, always true, is that momentum is always conserved. And what that means is that the total momentum of a system is always the same, right? So that's what that symbol means here. The change momentum for a total system is 0, or the total momentum stays the same, right? I already mentioned the weird ways that people use momentum all the time in language. And so, yeah, momentum is yet another 3 variable equation. So determine the momentum of a Pacific leatherback turtle, a mass of 8.6 times 10 to the 2. That's very specific. Swimming at a velocity of 1.3 meters per second forward, and apparently it's the largest species of turtle. All right. So, you just look at this and you think, okay, well, what relationship do I have between mass, velocity, and momentum? Obviously, it's momentum equals mass times velocity. So absolutely kind of look at those concepts given and use that momentum equals mass times velocity. Notice that this is a vector quantity. Momentum has a direction, and so it's a vector. So in this case, we're just putting the mass value in for m and the v value in for v. I'll have to kind of go like that, whatever. And so it's just substituting in, calculating out. Okay, so there you go. You get the value. And then, of course, with any 3 variable equation, there's the other 2 versions. And so in this case, we're given a mass of 4 kilograms. So given we have mass is 4 kilograms, and we're given the momentum is 18 kilogram meters per second. It's implied to be forward or in a particular direction. So for the vector aspect of it, and then we're asking what the velocity must be, right? So very similar stuff. You'd look at this and say, oh, I know a relationship between those quantities, those concepts. Momentum equals mass times velocity. Start plugging numbers in. 18 for momentum. I'll say the whole word maybe once in a while. And then the 4 and the v. And then we just have to divide both sides by 4. Right? So don't make the low level like grade 9s, and grade 9s often do this where they'll look at how the original question was done. Oh, the numbers we gave went in here and here, right? And so they just do that again. And so I'm working with my grade 9, so it's on my thoughts right now about Ohm's law. The numbers don't just go in for the current and the resistance every time, right? Anyway, so we would have to do the 18 divided by the 4. And so I'll just run the number for that. 18 divided by 4 gives us 4.5. And so we say, okay, that means we have a velocity of 4.5 meters per second. I almost wanted to say volts because I just talked about Ohm's law. Anyways, therefore stuff, right? The velocity must be that amount and a forward still, and of course, and so on. In the next one, let's look at what we're given. We have an object with a momentum given. So momentum is actually last time too, didn't I? So kilo 30. Sorry, thought I had the units wrong for a second, but it's the momentum is 30 kilogram meters per second. Also gave the velocity. It's 400 meters per second. It was right in the first place. Tried to squeeze in kilograms, but not for velocity. And we're asking for the mass. Okay, so as usual, analyzing what relationship there is between the concepts, and that is, of course, the equation. And we plug numbers in. So we have the momentum of 30, and we have the velocity of 400, and the mass is unknown. And don't really need a bracket there, but you could have, it feels good. And dividing out the 400 gives us a mass of, okay, so 30 divided by the 400. 30 divided by the 400. Obviously, it's going to be like 7 fives, right? So 0.75. That would be in kilograms. So again, therefore, blah, 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 right? The mass would be 0.75 kilograms, so 75 grams. In other words, if you had 75 grams going 400 meters per second, it would have 30 units of momentum. That's quite often what people would say, by the way, 30 units of momentum rather than 30 kilogram meter per seconds of it. So there you go so far. What else do we have here? So impulse, the other aspect to do with this, and this is where the really important part comes in for safety, as you'll see. So impulse is defined as the change in the momentum of an object. Okay, so I don't know if you're in tune with this enough where I've said that the momentum is always conserved, but now I'm talking about change of momentum. And of course, the momentum of a whole system doesn't change, but individual pieces can change momentum, obviously, right? And so we'll see how this works out. But think of like if you are on a boat and you and the boat as a system have a combined momentum. You all of a sudden start running towards the front of the boat, especially if it's something like a canoe. Picture the canoe going backwards, you going forward to some extent. Overall momentum of the system is the same. Okay, so there's going to be questions like that in our work later on, not quite yet. So anyways, we have forces acting on for an amount of time and a mass. It causes acceleration and changes in velocity. So therefore, you're going to get a change in momentum, right? And so, I think of the idea here where you're going to have your momentum being the final momentum minus the initial momentum, right? So you could think about that m delta v logically being as making sense as well. But I mean, if you have a change in velocity, you're going to have a corresponding change in momentum. So either way you look at it, should make sense. And then let's look and see what's making that happen. We have this idea of force times time, right? So, oh, by the way, I wasn't supposed to reveal that yet. That was supposed to be the ta-da moment at the end. So we have force equals mass times acceleration. 1 second here, I'm just going to pause. All right, we're back. So we know that F equals ma, force equals mass times acceleration. Acceleration is delta v over delta t. So if you look, you actually have change of momentum, right? M delta v is your change in momentum. So we have this F net equals change in momentum divided by delta t. So really we have change of momentum is F delta T, right? So what we have is this, idea here, force times time is your change of momentum. So that's an important concept, equation, relationship, and so on. Now, if you notice, if you have a change in momentum, that can be because of a large force for a small amount of time or a small force for a large amount of time, right? So let's just go through theorem. This video for us. Bear with me for a second while I put my video disc in. All right, so impulse, probably I can just search here. Oh, there it was, but back to it here. We had it. Impulse. Oh, I must be wrong. Helps if I spell it right, I suppose. All right, there we go. So, impulse momentum theorem. So just some demonstrations done by this guy here about things that are important for this. Use of it shortly here.
We're going to be looking at some applications of the impulse change of momentum relationship. Now, according to that relationship, impulse is equal to the change of momentum. As an example, suppose that I drop this brick to the table. Now, in the collision, the brick underwent a change of momentum. That's its final momentum minus its initial. The final momentum is what it has now when it has come to a stop, so that's zero. The initial momentum is what it had at the instant that it hit the table. And that depends upon how far I dropped it from. Now, if I were to drop the brick on this cushion, its change of momentum would be the same as it were for the table, because the brick comes to a stop. That's its final momentum, which is zero. And the initial momentum is
So
what
if it was dropped from the same height, it's going to have a velocity that it hits the sponge with, right, the foam with. And so because it collapses a little bit, that change of momentum is going to take a little longer, which means there's going to be less force between the two. So if you drop the brick on your hand on the table, it's going to hurt a lot more than if you drop the brick on your hand against the sponge, or the foam, because it can collapse, right?
At the instant it hit, and if I drop from the same height, that's the same as it was for directly on the table. What is different in these two cases is the amount of time that the collision lasts. In the case of the cushion, you can see that the cushion depresses. You can see the cushion compress, and that takes more time than if I drop it directly on the table. So you can see what the purpose of a cushion is. That's the cushioning effect that you get, is basically it's increasing the time that the collision lasts. When you walk across a carpeted floor, you have the same sort of a situation. For each step on the floor, you feel less force than if you were to walk across a concrete floor, for example, because the duration of each collision is less. Another example of that is when you jump from a height. When you hit the ground, as you hit the ground, you always
bend your going for it, like, in the name of science here.
Knees. That's essential if you want to protect your bones. Because by bending your knees, it makes that collision last a lot longer, and as a result of that, the force of the impact is less. If you didn't bend your knees, you'd do serious damage to your bones and to your joints. Now, we can apply the impulse momentum relationship to another situation where, in fact, we want to make the force as large as possible. When you pound a nail, you want greater force, not less force. When I drop the hammer on the head of the nail, the hammer undergoes a certain change of momentum while it's colliding from whatever it had at the instant it hit to zero when it comes to a stop. So again, that side of the equation is fixed. So if I pound with the piece of wood on the table, my collision is going to last a lot shorter time than if I pound with my block of wood on the cushion. Obviously, you'd never try doing something like that. That makes the collision last too long, and so the force is going to be correspondingly small. You always have a hard surface underneath it. That makes the collision last for a shorter period of time.
So another situation where you might have discovered or found that kind of thing is if you're trying to hammer a nail, maybe you're building a fence, right? The nail at the bottom of the fence is a lot easier to drive in than the nail at the top if the fence, is a bit flexible. So you kind of hold the fence steady to try to, allow it, force it to not move. You could take a brick or a rock or something and put it on the other side of the fence too. And then the inertia of the mass that you put behind the fence would make it easier to drive that nail in, right? So if you ever experience that, that's why, right? It's a really impulse and momentum connection that certainly can be made. So, like we said already, you can have a change in momentum due to a large force over a small amount of time, or a small force over a large amount of time. All right, something else, it's kind of it keeps coming up all the time, right? We can always look at graphs and get values. And so if you look at a force time graph, kind of valuable to think of that because the area would be force times time, which would be your change in momentum, right? Your impulse or your change in momentum. And so the shorter the time interval, like if we wanted to have this area represent the change in momentum, right? If we had a shorter time interval, how tall would that rectangle have to be to have the same area, right? The larger the force would have to be to get that same change in momentum, right? So that's a nice visual of that idea. Now, smart car silly clip. Let's go to that one. So here we go. So they've got a smart car. I think they're running it by remote control. They're definitely running it by remote control, blasting along at a good speed, and right into a big cement barrier. Just, obliterated.
From 70 miles an hour to 0.
So they're going 70 miles an hour to 0 in the blink of an eye, right? That's a huge change in momentum. It means there's a huge force involved, okay?
In 1 second, Little Smart hit with such energy that it moved 20 tons of concrete, leapt into the air, and rebounded to the side of the road. We didn't know what we'd find when we reached the wreckage. The steel cage has certainly done its job really well.
So he's talking about the steel cage. He's talking about how rigid, how strong this structure is.
You can still see the original shape, just that one nasty kink there. Don't forget, this is a car without a roof. The plastic was just shattered. So without even the strength of the roof, there hasn't been that much effect. You can open the door. Bits fly out. And so when you come around the front, you do see that massive impact. Around the other side, though, it still looks remarkably like a smart car. You can see the full shape of the door. Indeed, the door not only opens normally, closes again. That does show how well that cage has worked in the
It shows how well that cage worked. Yes, it does. Now, I'm going to watch this one next, your smart car crash test. I'm just going to go where this is. Smart car crash test. We're going to watch the first 50 seconds.
The key to its defences is its so-called Tritium safety cell, a rigid steel cage reinforced at key points. Smart described it as the hard shell of a nut, with small but efficient crumple zones both at the front and at the rear. In theory, getting inside is like putting on a suit of armour.
We're going to come back to this video. Watch this part really carefully here.
Even when it hits something more than twice as heavy, the bit where you sit is remarkably unaffected. There may not be a long crumple zone, but look how the Smart's windscreen remains intact. This is testimony to the rigidity of the passenger cell.
Now, what we're going to look at there, and I'll remind you of, but I want you to maybe go back, follow the link, and look at it again. But I'll say in the video later on, if you watch the car, the big car keeps moving to the right, and the smart car stops and starts going the other way. That's critical here. But after watching that first 50 seconds, is it really good to have that rigid cell? Right? Is that a good thing? Right? So this is the part I'm talking about how if you go and you look at this, so it says this small but efficient crumple zone. You need space, right? You need big crumple zones to allow for longer collision times, and therefore a smaller force, right? So it's just kind of against the possible, the possibilities of physics to say, oh, it's a small crumple zone, but it's efficient. Like, okay, what does that mean, right? What's the efficiency mean? In the crash, the large car, right, is still moving to the right even after the smart car has stopped and started moving the other way. The person in the larger car would have a much less momentum change over that amount of time, and a more gradual momentum change. Therefore, less forces and less chance of injury. So after the 50-second mark, if I just play it a little bit more, you can see like they do acknowledge some actual physics, but they use some buzzwords like talking about types of technology they've put into it to try to mitigate the fact that what they're talking about doesn't make sense, right? This rigid cell protecting you doesn't make sense. Really, all it's going to do is make it easy to open that door to remove the human inside that is in not good shape. Because of those extreme forces that would have been transferred to that person by that rigid cell, rigid protective cage. And I'm doing air quotes around the word protective.
Downside of the shell's rigidity is that there's a greater potential for the crash forces to be transmitted through to the passengers.
So she said that's the downside of that rigid cell, is the force transfers to the passengers.
Ideally, you want to slow them down as gently as possible. So you get seatbelt tensioners that stop you lurching forward violently, and they're fitted with force limiters that give you a bit of slack before they dig into your chest.
So the seatbelts are designed to give some slack as you're slowing down, so that the seatbelt doesn't like slice into your chest because of the huge change of momentum you're going to endure. There's just it's just not good at all. Another one that we could look at here, I think is this. Wait, now I'm just going to follow the link. I forget whether this is just the same thing or not. It's probably going to make me watch an ad, though. Oh, there we go. Yeah, this is good. It's really the same kind of video, but yes, we're going to watch an ad about cows. Sure, why not? Uh-oh. Here we go.
Strong.
Oh, it wasn't about cows.
And free.
Here we go. So another video just like the other one where you have the car coming in.
Real life safety. This philosophy applies to all Mercedes-Benz and Smart.
So it's a Mercedes ad. They're going to show the smart car colliding. It'll start again here.
Smart versus S-Class. Looks pretty much like David versus Goliath. And they will collide to demonstrate their high safety standards.
So again, they're using this as a way to say like, oh, the smart car is so amazing.
Thanks to its Tritium cell, the Smart's passenger compartment remains intact.
See how this car is still moving to the left this time, and the smart car is stopped.
A hard shell
and going the other way.
But Daimler, safety is
bigger change in momentum is not a good thing for the passengers, right? So is this Tritium, whatever they're saying, good? It's really not a good thing at all. And like I said before, the door being able to open is really just makes it easier to remove the, unfortunately, probably dead body out of it. So not nice to think about. This is that force time graph, right? The effect of crumple zones, the effect of crumple zones, right? So if you have a bigger the crumple zone, the less force you need. So the area underneath that, because it goes out. So far, you can have a smaller force, right? So obvious physics of how something like this works. You've got airbags, and what do? They gradually slow you down instead of the first force of contact you're having from like the steering wheel or the dash or even the seatbelt. You're hitting against this big airbag that pushes on you for a longer amount of time, reducing the amount of force needed. All right. Well, calculation style question here. You have a certain mass and it has an average force on it. And it says determine the speed of the ball after the collision. The average force on it is for 4.5 milliseconds. All right. So we've got a force acting on it. So we got a force times a time basically. So we're going to get the change in momentum and therefore the change in speed. So let's delete here. So there we go. We've got numbers in for the, eventually numbers in here, I guess, right? They solved like they like to do, right, for the whole thing, but numbers go in and it's going to allow you to solve for this, for the speed. I would probably run the numbers slightly different way, but you can go back and pause it and so on to follow that. And then it says, you know, well, what about if the force acts for longer? Right? Well, if the force acts for longer, they just go ahead and use that same equation they worked out, and they show the final speed is faster, right? And so they're saying, hey, well, what is the advantage of follow through in your swing in tennis then? Right? The follow through means that the racket's going to be in contact with the tennis ball longer, and so you're going to have a greater final velocity, which is what you want in tennis, right? So, like I said here, I would probably just put numbers in the average force and the time and have the change in momentum, and then afterwards go change momentum equals F delta or M delta V, right? So just get your change in velocity that way, but it works either way. And just one other thing to show, you know, design and marketing, you know, some people get it and some people don't here. We have these two hockey helmet companies. We have Easton advertising their Z-Shock. You know, it's so rigid, you know, you can't even crush it. And then you have the Messier project by Mark Messier. I believe has had some concussions in his life. And his helmet design that he's marketing has crumple zones. It has these like, you know, air like zones inside the helmet that can squish as you're hitting, which is going to increase the amount of time that the change in momentum happens during, and therefore it's going to decrease the forces on you. That's a good thing. Less force on your head versus this Z-Shock business. You know, you don't have any flex at all, and so that force is immediately just transferring right to your, you know, making your whole brain, whole head, all of a sudden go whichever direction it's being hit. Possibly they might have, I don't know, it's just they're maybe they have cushioning inside of here too, but it's not what they're advertising at all. And so, yeah, I think this is a much better science behind the Messier helmet. It's just in analyzing the science of it. So there we go. All right, so that is it for that. Hopefully I don't get dinged with copyright things. Otherwise I'll have to redo this and post it on the site directly. Well, actually, I'll just post the video directly on the page, not on YouTube. So neither here nor there. Thanks for watching.